So if you remember from the last two classes, we are looking at the rectangular metallic waveguides. And then first we started with the transmission lines, and then we looked at the second application, which is the rectangular waveguide. And then for the rectangular waveguide, we saw that this is the general solution for our different field components, where kx square plus ky square minus gamma square is k square, which is omega square root of mu epsilon. And then we got these 4 boundary equations. And from these 4 boundary equations, we found our solution. And my solution for, so we looked at which solution? We looked at HZS solution, because as I told you, with this, you would be able to get the other components. And moreover, as I told you, we are looking at the TE modes. So therefore, for the TE, you will have the 5 field components, which are this one, where it is, okay, it is not here. So 5 field component, which will be HCS, EXS, EYS, HXS, HYS, and HZS, which is this one, because EZS will be 0 in the TE case. And then we applied the boundary conditions, and we saw that this is our solution, where it is this one. This is our solution, which is H naught cos kxx cos ky by e power minus gamma c. And then we also found that this is the solution, but when we apply the second, the third, and the fourth boundary condition, we saw that there are several solutions of kx and ky which will satisfy my HZS. And those solutions depends on the kx value, because kx is m pi over a, and similarly ky is equal to n pi over b, where m and n, m can take values from 0, 1, 2, 3, n can take values from 0, 1, 2, 3. And this is what I told. So if you see your rectangular waveguide, if this is my 0a and 0b, then you have seen, if this is my x and this is my y, I explained it to you that as the value of m changes or n changes, here the sinusoidal variations will change. So for m is equal to 1, you will have 2 extremes here. See, this is an extreme, this is an extreme. For n is equal to 2, you will have something like this, and so on. So that's why you will get different patterns based on what is your m and what is your n, or I would say what is your kx and what is your ky. For ky also, it's a similar thing. For ky, it's in this direction. So this is for n is equal to 1. And as you change, this is for n is equal to 2, and so on. Okay. So then if you remember, then we moved ahead, and then we saw what is called as a cutoff frequency. And as I told you, our rectangular waveguide cannot allow all the frequencies to be propagated. It works as a high pass filter. And to find what is the cutoff frequency, what we did, we first got our gamma, because we know our kx and ky value from my boundary condition. See, for my boundary condition 3 and 4 that I substituted here, and this is my gamma, the propagation constant. And for the cutoff frequency, that means the frequency which doesn't propagate, my cutoff frequency, my gamma is equal to 0. So if I put gamma is equal to 0, and in place of my omega, I am putting omega c, because this will correspond to my cutoff frequency. That's why. And then when I simplify, I see that this is my cutoff frequency. That is omega square, omega c square mu epsilon is equal to m over a square plus n over b square. And from here, you can replace your omega c as 2 pi f c square right? And then further simplify it, you will see that this is my expression of the cutoff frequency. In terms of what? In terms of M, in terms of N, in terms of A, B, which is the dimensions of my rectangular waveguide, and mu epsilon, which is the material, the dielectric material. So what does this mean? This means that you can design your rectangular waveguide just by proper selection of your dielectric material and the rectangular waveguide dimensions. Then you can get your cutoff frequency. And we know that 1 over root of mu epsilon is nothing but is my phase velocity u dash. So here guys, whenever I use dash, that means it is for the unbounded medium. That is, you are in the same dielectric material, but it is now no longer has the conducting walls. It is unbounded medium. So that we say we represent it with dash. So dash usually represents, because further in other class also, or in the subsequent discussion also, we are going to use dash. So dash always means unbounded medium. It is unbounded medium. So I'm replacing it with u dash. So this is my cutoff frequency, which is u dash over 2 root of m over a square plus n over b square. So where m can take 0 to 1, n can take 0 to 1, but as I told you, both cannot be 0. See here, if both become 0, that means there is no cutoff frequency, which cannot happen. And u dash, as I told you, it's for the unbounded. Now, let's say, look at the two cases. So what are these two cases? The first case is called as the evanescent wave. Evanescent wave is nothing but we say it as a wave which is below the cutoff frequency, that is not propagating. So if f is less than fe, if my operating frequency of my signal or of my electromagnetic wave operating frequency is less than the cutoff frequency, then what will happen? So if my operating frequency is less than cutoff frequency, that means in angular frequency also it is less. Then if you see here, my gamma square will become greater than 0. How I'm getting gamma square? See here. So this is my omega c square. Can you see this? This is my omega c, the cutoff frequency, omega c square root omega c square mu epsilon. Now what I'm doing is I'm substituting this in my gamma value. So what you will get? Gamma square. So I'm substituting here. See here. So what is this one? This is omega c square mu epsilon. So my gamma square is omega c square mu epsilon minus omega square mu epsilon. So this is what we are doing here. So my gamma square is omega c square mu epsilon minus omega square mu epsilon. So this is my operating frequency f, and this is the cutoff frequency of my rectangular waveguide, which is decided by the dielectric material, the dimensions, and other things. So if omega becomes smaller than omega c, see, then my gamma square becomes real, greater than 0. Oh, that means my alpha plus j beta is now real. In that case, what should I say? What should I conclude? Yes, Basil, can you tell me? If gamma becomes pure real, becomes greater than 0, then since we know that this is equal to alpha plus j beta, so what should I conclude, Basil?
Beta is equal to 0.
0, yes. So in that case, alpha is not equal to 0, that is alpha is greater than 0, but my imaginary part is 0, that is beta is equal to 0. That means my phase constant is 0. And this is telling me that the wave decays in the direction of propagation and hence does not propagate. So If I select a frequency, a microwave frequency, which is below the cutoff frequency of my rectangular waveguide, then that particular frequency electromagnetic wave cannot propagate because this will happen. Evanescent. Then that's why it is called as evanescent waves, decaying waves. So it will decay along the direction of propagation and then it will die. The second one is propagating waves. So what do you mean by the propagating waves? In the propagating waves, that means these are the waves which are above the cutoff. So that means my frequency of operation of my electromagnetic wave is greater than the cutoff frequency. So in this case, gamma becomes less than 0, or gamma square becomes less than 0, because gamma square is omega c square mu epsilon minus omega square mu epsilon. See, so it becomes imaginary, it becomes pure imaginary. So in this case, alpha becomes 0 and my beta, which is my imaginary term, is no longer 0. In this case, we say that the wave propagate without decay because my alpha is 0. And the wave is called as the propagating wave or guided wave. This is a very important word, very, very commonly used in rectangular waveguide. They are called propagating waves or propagating or guided waves. Propagating waves, guided waves. And as I told you guys now that we don't use waves mode, we use modes. We use modes. Commonly in rectangular waveguides, we use the word modes. Now come here. So TE modes, they are labeled using the value of M and N, like TE subscript M. So for instance, TE23, what does this mean? This means that this is my M, which is 2, and this is my N, which is 3. And this is actually giving you the type of pattern which is created. Because as I told you, as we know, that as M or N changes, the pattern will change. Because if you remember, this is what we discussed here. See, when M becomes 1, the sinusoidal pattern will be different. When M is equal to 2, the sinusoidal pattern along the X direction will be different. So this is nothing but these are called different modes or different patterns that you see in the transverse direction, which is in the XY plane, because my Z is the direction of propagation. So XY plane will see these kind of patterns. So all these patterns, they are differentiated with the help of this subscript M and N. Okay, and those are called as TE modes. So now let's take an example. The example is saying that you have a rectangular waveguide of dimensions 5 centimeters by 4 centimeters. The waveguide is filled with a non-magnetic dielectric. So you have a non-magnetic, which is mu r is 1, and a dielectric material whose dielectric constant or relative permittivity is 2.25. And we need to calculate the cutoff frequency of this particular mode, TE2, 3. So how should we go? How should we proceed? So we know the expression of the cutoff frequency, which is this one, remember? So the cutoff frequency is U dash over 2 root of M over A square plus N over B square. So here you need to first find U dash, which is the phase velocity of the unbounded medium. So first I'm finding U dash, which is 1 over root of mu epsilon, which we know that it is C over root of mu r epsilon r. Substitute. So this is U dash, and then put it in this expression. So U dash over 2 root of M is what? See here, this is my M, which is 2, and N, which is 3. So 2, 3 divided by A. A is what? The dimensions. So the dimensions was given to you. A is 5 centimeters, but we always put it in meters. Okay. So you have to unify the units. So it is 0.05 meters and B is 0.04 meters. If you substitute here, you are seeing this as the cutoff. see, which is 8.5 gigahertz, which is in our microwave frequency. Now, what does this 8.5 gigahertz is telling you? This is written here. That means if my operating frequency, okay, if my operating frequency F is less than 8.5 gigahertz, that means the TE2,3 mode is evanescent. That means TE2,3 mode cannot propagate, or I would say it cannot exist. It cannot exist in your rectangular wave. If my operating frequency is less than 8.5, because the cutoff frequency of my TE2,3 mode is 8.5. It does not exist. But if my operating frequency of my signal, which the microwave signal, which I am using to say generate my electromagnetic wave and transmit through my rectangular waveguide, if that operating frequency is greater than 8.5 gigahertz, that means my TE2,3 mode exists. That means it becomes it can propagate, and it is called as a guided mode. So this is for TE2,3. So now, it's obvious. It comes in my mind that what could be the smallest possible cutoff frequency? Because remember, guys, this is the cutoff frequency. This is the cutoff frequency for this particular mode, which is 8.5. Can we find the least cutoff frequency value that your rectangular waveguide can support? The least value? This is what we are now trying to do. How can you get the least value? We know that this is my expression of cutoff frequency. Now, what could be the least values that we can put here? So the least value comes from M and N. So what could be the least value of M and N you can put? Yes, Mr. Abdul Mohsin, can you tell me? So what should I put? Should I put M is equal to 0 and N is equal to 0 because these are the least values? Remember?
Yes.
So should I put M is equal to 0 here and N is equal to 0 here?
I think so.
Okay, so if I put M is equal to 0 here and N is equal to 0 here, then my FC is becoming
0.
0. So that means FC is 0. That is, my cutoff frequency is 0. What does that mean? That means no frequency can propagate through the rectangular waveguide, which is incorrect. So that's why I am again re-emphasizing. If you remember, Abdullah, I told that your M and N cannot be 0 together. Got it? So M and N cannot take 0 values together. They cannot take it 0 values together. So now comes the next one. So what should be the smallest value we should take for M and N? So should I take M is equal to 0 and N is equal to 1, or M is equal to 1, N is equal to 0? Maybe Mr. Ahmad Al-Ghazwi, can you tell me which one should I use? Ahmad Al-Ghazwi.
Yes, M1 equal to 1 and N equal to 0.
Why? Can you think about it? Why we have to take this? I know it is written here.
To make it
So if I make M here 1 and if I make N here 0, so why I'm taking this? Why not I'm taking the other way around?
so we could end up with the rest as it is written here.
Sorry? Yeah, lowest possible. Yes, yes. Yeah, Hassan. But how we are getting it lowest possible here? Yeah, we end up with the lowest possible. I know. But I'm thinking from here, mathematically, you will just look at it and tell me how you are getting it. It's just a simple mathematics. Just to look at here, look at the ratios. Yes, Mr. Abdul Majid Al-Mutairi, you raised your hand. Can you help?
Yes, doctor. We look at A and B. We look which number is the biggest one.
Exactly.
And we take the coefficient of it is equal to 1. So we get the minimum number.
Exactly. Correct, Mr. Ahmed Al-Ghazvi, because we need to look at A and B. So since in our case, A is greater than B, that means this value is larger than this value, right? So if I make this one, then the ratio will become smaller than this one. So because if I take this as 1, so 1 over B ratio will be greater than 1 over A ratio. Why? Because A is greater than B. That's why we take M is equal to 1 and N is equal to 0. Clear? Yes, Taha.
So does that mean changing A and B, the dimension, only change the dominant mode, which is
It will, yeah, it will change the dominant mode, and it will also change all your field components as well. And that's the reason, Taha, when we started our derivation, was our assumption that A is greater than B. Because when you make A is less than B, yes, you can see here the cutoff frequencies changes, and you will see later when we look at different field components. You will see that different field components are all function of this M and M's. So they are all, field components will change. That's why. Okay. So let's continue. And now if I put M is equal to 1 and N is equal to 0, this is my answer. U dash over 2A. That means your least cutoff frequency is dictated by your longer dimensions. And this mode, TE1,0 is called the dominant mode. That is, this dominant mode has the least cutoff frequency, and that least cutoff frequency value is this. That is, this is the first mode that becomes propagating as my operating frequency increases. So when the operating frequency of my source, when I start increasing, the first mode which becomes propagating in the waveguide is my fundamental mode. This is called as dominant mode. It is also called as fundamental. This is the first mode which becomes propagating. Okay. So this is F cutoff frequency is U dash over 2A, and this TE10 is called as the dominant mode. So let's take an example. So the example says that you have a rectangular waveguide and its dimension is 3 centimeters by 2 centimeters, and it is filled with air. So here the medium is air. Very similar to our experiment 8 and 9, because our rectangular waveguides in experiment 8 and 9 in the lab, they are filled with air. Now we need to calculate the cutoff frequency of the dominant mode. And also we need to find the cutoff frequency of TE11. Then it is saying that if my frequency of operation is 9 gigahertz, then we need to check whether TE10 is a propagating mode or an evanescent mode. And if my operating frequency is 9 gigahertz, is my TE11 a propagating mode or evanescent? And last one is, below what frequency does the waveguide not support any propagating mode? So what is the frequency below which your waveguide cannot support any propagating mode? So let's start. So calculate the cutoff frequency of the dominant mode. So FC TE10 is U dash over 2. And what will be U dash here? because my dielectric medium is air. So therefore we know for the dielectric medium air, your phase velocity U dash, which is for the unbounded medium, is nothing but so the velocity of light. So it is 3 times 10 power 8 over 2 multiplied by 0.03 is 5 gigahertz. Then the cutoff frequency of TE11 mode. So TE11 mode. So this is U dash over 2a root of, remember, m over a square plus n over b square. So m is 1, n is 1, this is a, this is b. So it is 9.013 gigahertz. So now the question is, if my operating frequency, the third one, if my operating frequency is 9 gigahertz, is my TE10 propagating? Check. This is my operating frequency F. So my operating frequency F, is it greater than the cutoff frequency of my TE1,0 mode? Yes. See, this is the cutoff frequency of TE1,0 mode, 5 gigahertz. And my operating frequency is 9 gigahertz. So therefore 9 gigahertz is greater than 5 gigahertz. So therefore, your TE1,0 mode will exist. It will propagate in the waveguide. If my operating frequency is 9 kilohertz, that means I have selected a source signal, a microwave signal of 9 gigahertz frequency. And now I'm shooting it into this rectangular waveguide. So what will happen? This electromagnetic wave of this 9 gigahertz, it will propagate. And it will propagate because it will propagate using this mode, because TE1,0 mode cutoff frequency is 5 gigahertz, which is less than 9 gigahertz. So therefore, your electromagnetic wave that will be existing inside the rectangular waveguide will be TE1,0 mode, and this pattern will be carrying your energy or the electromagnetic wave of that source. Now, if frequency is 9 gigahertz, what about TE1,1? Will it be propagating or will it be evanescing? Again, check. Is my frequency F greater than the cutoff frequency of my TE11 mode? If it is greater than the cutoff frequency of TE11 mode, then yes. Then my TE11 mode can exist and it can become a guided mode. But if my operating frequency is less than the cutoff frequency, that means we do not have enough frequency to excite the TE11 mode. So here my frequency F is less than 9.0139. See, it is less. So therefore it cannot excite. Therefore your TE11 is your evanescent mode. Got it? And the last question was, what is the minimum frequency? Below what frequency does the waveguide does not support any propagating mode? So what will be this frequency, guys? Muhammad Al-Hazmi, can you tell me what will be this frequency? The frequency at below which your waveguide will not propagate any mode.
5.
Sorry? What will be the frequency below which your waveguide will not support any mode? So Muhammad Al-Hazmi, think from the dominant mode, because dominant mode is the mode that will have the least cutoff frequency, right?
Right.
Your TE1,0 mode is your dominant mode. Dominant mode.
5 giga, Doctor, I think.
Yeah, it will be less than 5 giga.
Yes.
Has the least cutoff frequency. Has the least cutoff frequency, because this is the first mode this will become available, or this will exist and it will propagate. So it will have the least cutoff frequency. So any frequency less than the cutoff frequency of TE1,0 or equal to TE1,0 your waveguide will not be able to support. It has to be just greater than 5, because this is your 5 gigahertz. And this is what we mentioned here in E, that it should be less than. No propagating modes. Okay. So all the modes becomes evanescent and the waveguide does not allow any mode to propagate through it, even the dominant mode. It has to be just greater than 5 gigahertz. Okay. So I think here we will just stop and we will take 2 poll questions. So if you guys are ready. So very simple poll questions again. So one is from our transmission lines. So here comes, and since it is true or false, I'm not going to give that much time, just say 40 seconds. So here it is. It says that in a 2-conductor transmission line, your G and 1 over R, G is equal to 1 over R, where J is the conductance and R is the resistance per unit length. Is this statement true or false? G is equal to 1 over R, where G and R are the line parameters. G is the conductance per unit length and R is the resistance per unit length. So 5, 4, 3, 2, 1, and that's it, guys. So what is the answer? True or false? Yes, Mr. Maybe Thabit, can you tell me what is the right answer?
It's true, doctor.
It's true. Well, guys, I will share the results, but I'm not happy. It is false. Guys,
Yeah, there are L and C.
no, not L and C. If you remember, guys, I told you that G is of the dielectric medium and R is for your conductor. These are 2 separate parameters. G is not equal to 1 and R. They belong to 2 different parameters, 2 different materials, I would say. Transmission line. If this is my conductor, then R is coming from here. R is 1 over sigma, which is coming from the conductivity of my metal here. This R is the resistance per unit length is coming from the conductor, and it is coming from the resistivity or the conductivity of my conductor, which is R is 1 over sigma or rho 1 over sigma. And the second thing is G. G is the conductance, and the conductance is coming from where? Is coming from this dielectric material which is between them. This dielectric material. This dielectric material, it's not perfect. So it will have a small conductivity, and that will make a leakage path between these 2 wires. That is the positive carrying and the negative carrying. It will create a small leakage path because of that conductivity. And that leakage path we are referring as G. So G is nothing but the conductance. And here, this is sigma of the dielectric. And this is for the conductor. And I have emphasized this several times, and that's why we put a resistor here. And this resistor is R. That I have emphasized this several times. The conductance is different and R is different. Just logically think, when we are defining the transmission line parameters, why we are defining G and R separately. If G becomes 1 over R, which was your poll question, then why would I keep G and R separate besides L and C as the transmission line parameter? If they are equal, I will not put that, right? Yes, any questions on this or any comments on this? Okay, so stop sharing the results. Let us go to 5. Okay, so this is again 30 seconds, very simple. Our rectangular waveguide, can it support all transverse electromagnetic, transverse electric, and transverse magnetic waves? TEM, TE, and TM waves. 10 more seconds. 5, 4, 3, 2, 1. And I think that's it, guys. So what is the answer? And maybe Sultan, can you tell me what is the answer?
I actually answered with true.
No, Sultan, it is false, because when we started our class, I told, right? When we started our class, if I'm not mistaken, I told, and in the last class, I explained it in detail that TEM is not supported by the waveguide. And this is why, this is because of boundary conditions, the 4 boundary conditions of this wall, this 4. So it doesn't support this one. It only supports TE and it supports TM. TEM is in the unbounded medium. That is unbounded medium, traveling in air or any dielectric. Yes, there TEM wave exists. In fact, only TEM wave exists. TE and TM cannot exist there. Well, so majority is 16%, so at least I'm happy. But guys, please, I am telling you, we have our final exam, the very next day. So please, I would appreciate, I would encourage you to start preparing. And this poll questions, several, I have seen feedback saying that, no, this is not good, this is very bad. I mean to say anonymous comments on the Google, on the Google's sheet that Google document that I put to give to take the students' feedback. The university is really going towards using new tactics or new say approaches to increase the retention that the students, retention means what you remember. So these were considered as one of the ideas that we can try. Go and ask questions in the class and ask previous lecture questions, very simple questions, and see how students are able to remember that. So I'm asking very simple questions. I'm not asking very difficult questions in the poll. Well, anyways, so let's continue. So now what we are doing now is the following. So this is the complete summary. So if you see here, this is the complete summary of the last 2 classes, guys. So this is my HZS field component, how it looks like. It is cosine, where Kx is m pi over A, Ky is n pi over B. This is the cutoff frequency, and we know the dominant mode is TE10. We know if our operating frequency is less than cutoff frequency, then it is evanescent. If my operating frequency is greater than cutoff frequency, it is guided. So now what we are doing is we are now trying to find the phase constant of our propagating mode. So how? Again, we took this gamma expression, which is gamma square is omega c square mu epsilon minus omega square mu epsilon. And now I'm substituting my operating, instead of omega and omega c, I'm trying to get the expression in terms of f and fc. So if you see here, I'm doing some simplification, and then I'm replacing it with 2 pi f. This is with 2 pi fc, this is 2 pi f. And if you see here, I'm getting this as my gamma. So my gamma is omega root of mu epsilon, root of fc square minus f square minus 1, which is this one. And from this bracket, if I take minus 1 outside, I will get as root of minus 1, right? I will get root of minus 1. And root of minus 1 is j. That's why you see a j here. And as it is, and this is flipped. So it is 1 minus fc over f square. So this is my gamma in terms of f and fc. And from here, if I equate what I'm getting alpha as 0 and beta is this one, because my right hand side is only imaginary. So this is my beta. So this is my propagation constant of my guiding medium, which is for my guided modes of or my propagating modes. Now, what I'm doing here, I'm now saying that this one is beta dash. So this is beta dash, which is only omega root of mu epsilon, because this is my phase constant of my unbounded medium. Remember, this is for the unbounded medium. So that's why I'm naming it as beta dash. So therefore, the new phase constant of my guiding mode of my bounded medium of my rectangular waveguide is equal to beta dash root of 1 minus fc over f square, which is unbounded medium times this term. It is times this term. Okay. And in similar way, you can get the phase velocity also of my propagating mode. So phase velocity is u is omega over beta, omega over substitute beta as beta dash. And then if you simplify it, you will see omega omega cancels and you will get 1 over root of mu epsilon, which is nothing but u dash. And what is the u dash? We have already told u dash is nothing but the phase velocity of the unbounded medium. So whatever dielectric medium is filled in the rectangular waveguide, if you just remove the 4 walls, that becomes the unbounded medium. So this is 1 over root of mu epsilon. So what we are doing now, we are trying to get our phase velocity also in terms of the cutoff frequency and the operating frequency. We got beta in terms of the cutoff frequency and the operating frequency. So this is my u, is u dash over root of 1 minus fc over f square. So where u is the phase velocity of the propagating mode and u dash is the phase velocity of the unbounded. And you see here, your u is greater than u dash. So that means inside the waveguide, the phase velocity is larger compared to the unbounded. Similarly, you can get the wavelength. We know lambda is u over f, very well known. Lambda is u over f. This is for our bounded medium because u is the phase velocity of the bounded medium. So lambda is u over f, which is 2 phi over beta. Beta is also for our bounded medium. So therefore, this is for the propagating. Okay. Now for the unbounded medium is this one. So lambda dash is u dash over f. U dash is the phase velocity of the unbounded medium, or beta dash is the phase constant of the unbounded medium. That will give me the unbounded medium's wavelength. And this is the last thing, which is one, I know the cutoff frequency of my any mode, then I can get the cutoff wavelength as this. So the cutoff wavelength is nothing but u dash over cutoff frequency, not u dash, because this is just we are trying to find lambda and FC relationship. So it is U dash over FC. Lambda C is U dash over FC. So these are all what we already looked at in our, the chapter of our transmission of electromagnetic waves in free space. We have already seen all these things. Here we are just getting it for our bounded medium, which is our rectangular wave. And now let's take this example. Now the example says that we have an air-filled rectangular metallic waveguide of dimensions 5 centimeter by 2 centimeter, and my operating frequency 8 gigahertz. That means I'm generating a source of 8 gigahertz, and this source I'm transmitting it through this rectangular wave. Okay. Now what it is saying? Name all the propagating TE modes at this frequency of operation. So what are the different modes of TE which can exist in this rectangular waveguide, which will carry the energy of the signal? You need to name. Then you need to look at and find the beta, U, and lambda C of this particular TE2, 0. So how you should do it? So let's start. So we need to find all the propagating modes of TE, right guys? So we need to now change M and N one by one. So this is what we are doing. So first, we are looking at the dominant mode. So M is equal to 1 and N is equal to 0. And FC is U dash, which is over 2 root of M over A square plus N over B square. A is 0.05, B is 0.02. So it is 3 gigahertz. Now check, is my operating frequency greater than this cutoff frequency of my TE1, 0? Yes. Therefore, it is propagating. Then I'm keeping N same 0 and I'm changing M as 2. And then I'm getting 6 gigahertz. So 6 gigahertz is the cutoff frequency of TE2, 0. So my operating frequency F is how much? Yes. What is my operating frequency F? My operating frequency F is 8 gigahertz. So my operating frequency F, sorry. So my operating frequency F is 8 gigahertz, is greater than the cutoff frequency of TE20 mode. So therefore it is propagated. Now M is equal to 3 and N is equal to 0. Put it, I'm getting 9 gigahertz here. What does that mean? My operating frequency F is 8 gigahertz. Now, but this operating frequency is now less than the cutoff frequency of TE3, 0. So it is less, so it is smaller. That means this mode cannot exist. So that's why it is evanescent. Then what I'm doing, I'm keeping M as 0 and I'm changing N to 1. And then I'm continuing. So if I continue, M is equal to 0, N is equal to 1, then I'm seeing 7.5 gigahertz. And my operating frequency is 8, which is greater than 7.5. And therefore it is propagated. Then I'm keeping M is equal to 0 and I'm changing N to 2. Then what I'm seeing, it is becoming 15 gigahertz, which is very, very great, higher than my operating frequency of 8 gigahertz. So therefore it is evanescent. Then I make M is equal to 1 and N is equal to 1. Then this is my frequency, which is again greater than my operating frequency, which is 8 gigahertz. So therefore it becomes evanescent. So therefore we stop. So now the modes which are propagating for my operating frequency of 8 gigahertz is TE10, TE20, and TE0. So these are the 3 modes. What does that mean? These are the 3 patterns of my TE mode. which has different electric fields and magnetic fields, they will carry the power in the rectangular wave. And this will be the power carried. So whatever is your signal power will be carried among all these three modes together. So they will all be superimposing, carrying together along the wave. Okay. So for B, you need to calculate beta U and lambda C. So you can find first the beta dash, and then you can find the beta. Your cutoff frequency is known, operating frequency you know, substitute U and Z. Okay. So I think guys, we will stop here and we will meet on Sunday for our next class.
Doctor,
Okay.